Radioactive decay. Skip sections in reading titled Successive Decay Equations, General Equation, Propagation of Errors. Decay of radionuclides. Unstable nuclei undergo decay to achieve stability. By spontaneous fission, which is the heavy nucleus breaks down into two fragments, emitting 2 or 3 neutrons. Probability increases with the mass number. Alpha decay usually occurs with heavy nuclei. Alpha particle is a helium ion with 2 electrons, is removed, which contains 2 protons and 2 neutrons. Mass number is reduced by 4. Atomic number is reduced by 2. Here we have an image. Shows plutonium-240 with 94 is then alpha decayed to the helium, and it becomes uranium with the alpha particle of helium coming off of it. Beta decay occurs when a nucleus is neutron-rich, neutron converted into a proton. Antineutrino is also emitted along with the beta particle. May release gamma ray depending on the amount of energy. Bremsstrahlung can occur with beta particles. Electrons passing through matter are decelerated. Avoid by using plastic instead of lead when handling. Positron decay occurs when a nucleus is proton-rich, proton converted into a neutron. Neutrino is also emitted along with the positron particle. The range of position is short in matter, therefore at the end of the path length. Positron particle combines with electrons and are annihilated, releasing 2 511 keV. Energy difference between parent and daughter is 1.02 MeV positron, whereas electron capture is when there is energy difference less than 1.02 MeV. Electron capture is alternative to positron decay. Small neutron to proton ratio. Proton captures electron and decays into neutron. Usually occurs in the K-shell electrons. They have a high binding energy. When vacancy is filled, characteristic radiation is released. So here we have the image of beta minus decay. You start with carbon-14, which has 6 protons and 8 neutrons, and then the beta minus decay turns it into a nitrogen-14, which has 7 protons, 7 neutrons, but it also releases an antineutrino and an electron. So we start at carbon-10 for a beta plus decay for positron. The carbon-10 has 6 protons and 4 neutrons, and then the positive plus, beta plus, turns it into boron-10, which has 5 protons and 5 neutrons, and that sends out a neutrino and a positron. Here's an image of Bremsstrahlung radiation. How this occurs is the electron comes really close to the nucleus and then gets shot out the other side, but because it comes so close to the electron, it causes a radiation. Electron capture. Here we start with a carbon-11, has 6 protons and 5 neutrons, and then when we get an electron from it, it becomes boron-11 with 5 protons and 6 neutrons and gives us a neutrino. The characteristic X-ray. So in this instance, we see where an electron from the L shell goes in, hits the K, and then the K X-ray comes out. And that's what is a characteristic X-ray. Decay of radionuclides continued. Isomeric transition. Decay of an upper excited state to a lower excited state. Many decay processes are accompanied by isomeric transition. These include beta, positron, and electron capture. Difference between energy states may appear as gamma rays. Metastable states are long-lived isomeric states are referred to metastable states. Internal conversion. Gamma comes out of the nucleus but bumps with electron, most likely on the K shell. The gamma is totally absorbed and the orbital electron comes flying out. The Auger process. Characteristic radiation is produced. Electron tries to come out of an atom but bumps into an electron within the same atom and transfer all the energy to that electron and comes flying out, releasing the Auger electron. Here we have an image of the Auger process. Alright, so we start with the characteristics from the E1 at the M shell goes in and hits the E2 in the L shell. And during that process, the radiation that was caused from that characteristic radiation from E1 to E2, that radiation is what hits the E3 in the N and then knocks that out. So that electron itself is the Auger electron. Radioactive decay equations. The disintegration rate, which is the decay rate. The decay rate is equal to the constant times the number of radioactive atoms. The decay constant is equal to 0.693 over the half-life. Radioactivity says that it is also the decay constant times the number of radioactive atoms. I believe that one is wrong though. Alright, so for an example, a source of technetium-99 contains 2.5 times 10 to the 12th nuclei. You find the decay rate and the activity of the source. So to get the decay rate, we take the 0.693 and we divide it by 360 minutes because technetium-99 has 360 minutes of a half-life. We have to use minutes in these equations. We can't use hours. It has to be minutes. And then we're going to multiply that number by 2.5 times 10 to the 12th nuclei. And we're going to end up with 4.8 times 10 to the 9th disintegrates per minute. Now, to get the radioactivity, we're going to take that 4.8 times 10 to the 9th dpm, and we're going to multiply it by 1 over 2.22 times 10 to the 9th dpm. That is going to equal 2.2 millicuries. So this activity equation is always going to be your decay rate in dpms multiplied times 1 over 2.22 times 10 to the 9th dpm. That is the formula. Decay factors, post-decay factor and pre-decay factor, and then the constant, which is the decay. The pre-decay factor is equal to 1 over the post-decay factor. If the 5-day post-decay factor is 0.836, determine the 5-day pre-decay factor for the same radionuclide. To get pre is equal to 1 over the post, so 1 over 0.836 is equal to 1.196. The pre-decay factor example. Find the pre-decay factor for the 2 days for iodine 123. To get the pre-decay, we're going to take E to the 0.693 over 13.2 hours, because iodine 123 has 13.2 hour half-life, and then we're going to multiply that times the 48 hours to equal the 12.43. Determine the decay factor for 10 days for iodine 125. So we get the E and then up to the negative 0.693 divided by 60 days times 10 days equals 0.891, which is 89.1% of the original amount remains. Alternate forms of decay factor is 2 to the negative n. N is equal to time over the half-life. N is equal to the number of half-lives that have elapsed. Determine the decay factor for 5 hours of technetium-99m. So 2 to the negative 5 hour over 6 hour is equal to 0.561, which means 56.1% remains. Calculating decay factor for different days. Decay factor of unknown over the known. If the decay factor for 6 days is 0.893, what is the decay factor for 8 days? So we have the 0.893 with the exponent of 8 divided by 6 is equal to 0.860. Calculating the post-decay activity. The activity of time is equal to the activity at the original times E with the exponent of negative 0.693 times time divided by half-life. Radioactive decay equation. A activity at time is equal to the activity of the original times E with the negative exponent of the constant times time. So starting with 25 millicuries of technetium-99m, determine the amount of radioactivity remaining after 8 hours of decay. Activity is 25 millicuries with the E to the negative exponent of 0.693 divided by 6 times 8 is equal to 25 millicuries times 0.3969 equals 9.9 millicurie remain. The mean life was just the average life of a group of radioactive atoms. I don't know what that T symbol is, but it is equal to 1 over constant units of radioactivity. Now the only way I really remember this is 1 becquerel is equal to 2.7 times 10 to the 11th curie, and 1 curie is equal to 3.7 times 10 to the 10th becquerels. That's the only formulas I can remember from that, but you do need to know that 1 becquerel is equal to 60 dpm, and 1 curie is equal to 2.2 times 10 to the 12th dpm. And then you can figure out the milli and micros anytime. Those you just work out. Transient equilibrium. When equilibrium is reached in which the parent's daughter seem to have reached a point where the half-life appears the same. At this point, you will get maximum yield of eluate. The parent-daughter half-lives differ by 10 to 50 times. Example, molybdenum. In the case of molybdenum generators, it is 23 to 24 hours. I don't know what this is trying to say. Secular equilibrium, where in the parent-daughter pair, the parent has a much longer half-life, 1,000 times or more. In this case, the daughter will eventually reach a point where the rate of production equals the rate of decay. The half-lives of the parent-daughter differ by more than a factor of 100. Example being cesium to barium-137m. Again, I don't know what that is. Standard deviation and count rates. Standard deviation for a group of measurements indicates the precision of the measurements. The standard deviation is equal to the square root of the average. Standard deviations in the radioactive measurements indicate the statistical fluctuation of radioactive disintegration. Standard deviation. If we make a series of measurements repeatedly on a radioactive sample giving an average, 68 of all measurements would fall within one standard deviation, with a 68% confidence level. 95% of the measurements will fall within 2 standard deviations with a 95% confidence level. 99% of all measurements will fall within 3 standard deviations, and it is with a 99% confidence level. Standard deviation count rates. The standard deviation of the counts is equal to the square root of the number divided by time. So for example, a radioactive sample is counted for 8 minutes and gives 3,200 counts. Calculate the count rate and standard deviation for the sample. The count rate is equal to 3,200 divided by 8 equals 400 counts per minute. The standard deviation count is the square root of 400 over 8, which is equal to 7. So the average count rate is 400 plus or minus 7 CPM, counts per minute.